This is video 2 of our chapter 8, 9 AP review. Let's look at a few questions here, 18 through 22. I went ahead and put in 21.5 just to make sure we have 5 possible options, and that allows us to review some of the concepts. So these are bonding of different types of solids. So this is chapter 8, where we're talking about more at the macro level, how that's connected to the micro level. So A says, we're going to essentially pick one of these for each one of these options. We have a lattice of positive and negative ions held together by electrostatic forces. Electrostatic forces just means the forces from positives and negatives. Now this is true of ionic compounds. And ionic compounds, remember, are things like NaCl. You have a positive and a negative, and these are held together by a force. And the strength of that force determines things like the melting point, solubility properties, and so forth. So cesium chloride here is an ionic compound. Now recall that ionic compounds, what determines the strength of the force are two things: charge and size. Wait a minute. Charge and size. I should say charge. So the bigger the charge, the stronger the force. That makes sense. Now size, the smaller the size, the stronger the force. So a small size actually creates a stronger force. This is because lattice energy, which was what we studied, has this equation, Q1 times Q2 over R. And so you would multiply the charges and divide by the size. Because we're dividing by size, the smaller this number, if this is a tiny number, then we're going to get a high lattice energy, and that's the idea. So if you have, say, cesium chloride against something like sodium fluoride wins because sodium is smaller, fluoride is smaller than chlorine and cesium. And if you have something like calcium oxide wins because their charge is higher. The charge actually has a higher effect, a stronger effect, than does the size. All right, how about the second one here? B says closely packed lattice with delocalized electrons throughout. Now famously, metals actually have this characteristic. So you have a metal is defined as positive charges with delocalized electrons. So positive charges with negative electrons existing everywhere, I should rather say. And that's why metals conduct electricity very well, because these electrons can be moved easily, and they conduct heat very well. They're malleable because these don't really belong to each other, so you can actually deform metals quite easily. So that is the definition of a metal. C says strong single covalent bonds with weak intermolecular forces. So single covalent bonds, that would be a methane here. So here we have single covalent bonds. So you have methane, the methane molecule. And then you have another methane molecule. Each one, notice, has single covalent bonds. Remember, covalent bonds are these chemical bonds. Now, intermolecular forces are the forces between the two molecules. So these are intermolecular forces. And they're weak because both of these are nonpolar. We're going to look at intermolecular forces in much more depth in chapter 12 and 13 review. But this essentially matches up for methane. So these are molecules, nonpolar molecules. Nonpolar molecules. D says strong multiple covalent bonds with weak intermolecular forces. That would be the case for CO2. If you take a look at CO2, CO2 has 2 double bonds on every side of the carbon to the oxygen. So, and to get the Lewis structure perfect, you would get yourself like this. And between these, you also have intermolecular forces, and these intermolecular forces are also weak because both of these are nonpolar. And that's why that matches. The last one, and I changed this one up a little bit, go ahead and put covalent bonds, strong covalent bonds. Or you have something else, go ahead and put covalent bonds. So macromolecules held together with strong covalent bonds, that would be solids like silicon dioxide. And there's not many of these. Carbon, elemental carbon does this, elemental silicon actually does this. And what happens is you get yourself a macromolecule. Macromolecule means a huge molecule, in which the carbons, in the case of carbon, are actually connected to each other tetrahedrally, and it's like one huge covalent bond, non-stop covalent bond. And that's why diamonds are very, very strong. Silicon dioxide is glass, same idea. Silicon dioxide has silicon and oxygen and then silicon and oxygen, and they just keep binding in this way. So there are no intermolecular bonds. It's all about pure covalent bonds. So it's like a super molecule with covalent bonds, and that's how this works. So this is a good idea to review all 5 of these, and let's see if we can apply some of these concepts to a few of these questions. So number 22 says, which of the following diagrams best depicts an alloy of nickel and boron? So alloys are mixtures of metals. They are not compounds, they're mixtures. That's why alloys can be any percent. In fact, you can put 25, 75, 80, 20, any percent you want. We want nickel and boron. Now, if you take a look at the periodic table, boron sits right up here in the P block. Nickel sits somewhere here to the a little to the right of halfway of the D block. So we know that nickel is bigger than boron because it's 2 energy levels lower. So nickel, if you were to see the size of the atoms, nickel is definitely bigger than boron. Now that will right away give you the answer right here. However, let's analyze some of these. These are actually molecules, so this would be a molecular substance. You have individual molecules, and these would be the intermolecular forces. So this would be something like HCl, for example. It could be a representation. This is also an alloy, but this alloy has 2 atoms that are roughly the same. So maybe between nickel and, say, cobalt, the element right next to it. This could be an alloy between nickel and cobalt. But and this one right here would be your ionic compound. So this would be something like NaCl. So you have positives, negatives, positives, negatives, positives, negatives. That's the idea. All right, let's take a look at the next one as well. The next one actually applies the idea of charge and size to boiling point. So here we say, based on the data in the table on the right, which of the following statements provides the best prediction for the boiling point of NaCl? The data tells you the boiling point of sodium fluoride and magnesium oxide. Now notice that magnesium oxide has a much higher boiling point, and that's because the bonds are stronger between ions of magnesium and oxygen. This is mostly due to the fact that magnesium has a +2 charge, oxygen has a -2 charge, which creates that difference. So the charge actually is what plays the role here. The sizes of the atoms, if you take a look, magnesium is actually smaller than sodium, which works against it. Oxygen is actually bigger than fluorine, which works for it, but the charge is what makes the difference. Now, they also give you the ionic radii of a bunch of elements, and then it asks about NaCl. Now, because we know that NaCl and NaF versus NaF here have the same charges, it's all +1, -1, the charge is not going to be a factor. However, the size will be a factor. So, chlorine is below fluorine on the periodic table. Here's your periodic table. You got fluorine, and then you've got chlorine down below it, which means chlorine is bigger than fluorine. Being bigger, chlorine will have a weaker attraction. So if you have a bigger atom, the attraction, because you can say that the positive and the negative are now further apart from each other because the atoms are bigger. Because they're further apart, they don't have as much of an attraction. The closer the ions are, the stronger the attraction. So if we take a look at some of the answers, A is actually the answer. Here it says NaCl will have a lower boiling point because the Coulombic attractions are weaker in NaCl, and that is true. The Coulombic attractions are positive-negative attractions. They're weaker because chlorine is bigger than fluorine. It doesn't say that, but that would be the reasoning behind it. B says NaCl will have a boiling point between that of NaF. That's not true because the covalent character of bonds is intermediate. That's actually not true. C says NaCl will have a higher boiling point because the ions are spaced farther apart. In NaCl, it would have a lower boiling point because they're spaced farther apart. So that is actually where the mistake lies. And then this one here talks about energy required to transfer electrons. That's the reaction itself. This is before they become ions, so that one's out as well. All right, why don't we just do one more? We can do the very last one here. If we take a look at the very last one, 47, here it says, we'll do this one quickly. Which of the following diagrams best illustrates how displacement of ionic crystals results in cleavage and brittleness? So ionic substances are brittle, and brittle means they break very easily, and that's because they have ions. So if you take a look, this is the picture of brittleness. You have ionic forces here, which are keeping these together. That's why it's really tough to melt them, really tough to separate these. Melting points are really, really high. melting points. But then, if you apply force here, you were able to displace this chunk of it, and it goes down. Now notice the negatives and the positives line up, and then there's a lot of repulsion. That's why this thing breaks apart, and you got the two chunks that break apart, essentially. So this brittleness is due to the fact that ionic compounds have these charges, which upon applying a force, make the ions line up, and they split apart. This one won't happen. This makes no sense, where the positive ion just goes down. This is metallic. So this would be what metallics do, and the one below is actually covalent. So hopefully this kind of summarizes some of the higher ideas, higher level ideas, and we'll take questions before we take the quiz.